Good morning again, students. From last week, we were looking at current electricity. We looked at what is current, what is electricity, how current is generated through a conductor. And we delved a bit deeper into it, looking at like quantities such as voltage, current, resistance, that sort of thing. We even looked at power, electrical power, as it relates to how a voltage source or a power source provides electrical power to electronic components. Now this morning, we'll be looking at Ohm's law. It's a funny name, but it's actually someone's last name. Based off what the slide here says, it says George Simon Ohm. Yeah, someone's last name. And he was instrumental in really figuring out what it is that really makes circuits tick. And really and truly, it boils down to those three main physical components: voltage, current, and resistance. And we're going to look at how all three work together to make the circuits tick. Whether it be a simple circuit just connecting a battery to a motor or a bulb with a switch, or even more complicated circuits such as in your cell phone. The concept remains the same. Ohm's law tells us what is happening. And if you look at the diagram here, we see that we have V ascribed to the power source. We have I that indicates the current that is flowing. And we have R, and that's affixed to a circuit symbol. From last week, you would have been privy or been introduced to circuit symbols, and you would have known that circuit symbols are basically fancy symbols that indicate actual components within a circuit. All right? Now, when it comes on to circuit symbols, this is what we'll be going forward with. All right? So you have to be familiar with those symbols. Now, as it relates to what Ohm's law is saying, when electrical energy is converted to other forms, be it light from a bulb, heat from a closed iron, motion of a motor, it involves a voltage source pushing a current through a resistance and a load. So essentially, that's how all three are related. You got to have a power source that provides a voltage. That power source now in turn provides a current, and then that current, which carries the electrical energy by virtue of the charges flowing, will give or impart the energy to the load, which provides some level of resistance. All right? Now, when it comes on to Ohm's law established that the voltage applied across a load of fixed resistance R is directly proportional to the current through the component within a circuit. So essentially, when you're looking at a law in science is something that has been tried, tested, and proven true. And pretty much what he found, Ohm, was that once you apply a voltage to a load, which is of a certain resistance, because loads are basically resistant devices to current flow, once you provide a voltage to that resistance and the resistance doesn't change, then the current is said to be directly proportional. We get to that bit in a little further, but don't worry about the whole direct proportionality thing. Just know that the two are related, voltage and current, when you look at a constant resistance. Now, the Ohm law quantities that we mentioned earlier on. Voltage. It is a driving force for current and energy as it relates to, right, we're good. All right, so voltage is the driving force of current and energy for an energy source for circuit. It is measured in volts. Current is a flow of charge carrying energy from one terminal of power to the other over a period of time. It is measured in amperes. And resistance is the opposition to current flow as it converts electrical energy to other forms and is measured in ohms. So volts is the unit for voltage, and coincidentally, they have the same symbols. Current, the unit for that is amperes, and the symbol for that is A. And the unit for resistance is ohm, and the symbol for that is omega. It's a fancy Greek symbol. Greek symbols are regularly encountered within physics. All right? Now, as it relates to the equation for Ohm's law, remember last week when we were looking at different when we're looking at the different equations that are involved in electrical quantities, we said that we encountered the magic triangle. The magic triangle is essentially equilateral triangle, and the symbols for this voltage, current, and resistance are arranged in a fashion that you can easily find one if you know the other two. So based on what the magic triangle is being shown here, you would have V at the top, I and R at the bottom. Being at the bottom, that means that when you cover V, V is actually equal to I times R. When you cover I, VI is actually equal to V over R. And when you cover R, V is equal to R is equal to V over I. So based on what the PowerPoint is showing here, all three equations can be combined into one using the magic triangle. V is equal to IR, I is equal to V over R is equal to V over I. You must do your best when you're doing equations and when you're doing questions to try and see how best you can recall these equations. All right, so shown here, V is equal to IR, I is equal to V over R is equal to V over I. And that essentially is the Ohm's law equation relating all three. Now, on to what it means to be proportional. For electrical conductors to obey Ohm's law, the voltage across the load is directly proportional to the current going through that load, provided the resistance of the load remains constant. So that is what the Ohm's law statement can be reworded as saying. Now, what does it mean by direct proportionality? This means that if the voltage value is changed, then the current will also change in a corresponding way. Which means if the voltage produces a certain current, that is producing a certain current is doubled, then the current value will also respond in similar or like manner, which means it should double. So if you have a voltage of, say, arbitrary number 2 volts, and that produces a current of, say, 0.5 amperes. Remember your units? If you double that voltage to 4 volts, then the current, based off Ohm's law, should also double to 0.5 times 2, which gives you 1. Continuing, the same is true for if you reduce the voltage by half. The current will also reduce by half. So the same example, 2 volts produces 0.5 amperes. If you reduce the voltage by half, going to 1 volt, then that current value of 0.5 amperes must also or should also reduce by a half to 0.25. Now, as it relates to the proportionality, anything that is considered proportional in mathematics can be represented on what we like to call a graph. Graph consists of two axes, a vertical and a horizontal, y or x, and these quantities, voltage and current, can be plotted against each other once they have a proportionality thing going on. Now, when you plot these two, then you'll get some basic graphs, but interesting nonetheless. Now, a graph showing proportional relationship between current and voltage produces a straight line that passes through the origin of the graph axis. Now, what is this origin? The origin is essentially the point where y and x axis meets. So the line will have to come through where y and x meets, which is 0, 0 for those who know math. As it relates to a straight line, it's really just, as the name suggests, straight line that follows either diagonally, flat, diagonally the other way, but it's a straight line, not a curve, a line. The gradient of the graph line gives the value of resistance for the component under investigation. So for persons who know math, all right, let me just give a little reminder as to how the whole gradient thing works out. If you have a graph, I'll probably use the black, contrasts well with the white here. So if you have a graph, and this of course is the y-axis, this is the x, right? The graph line passes through the origin. The origin is here. All right, that's where the 0, 0 coordinate is. And say you have a line that goes like that. Right? Not best straight line, but hey, you get the gist. Now, for you to find the gradient, there are two ways persons normally do this, but it boils down to be the same thing. You take two random points, you go across, you go down, you go across, and you go down. Right? Now, this being the y-axis, this is taken as y2, that's y1, that's x1, and that's x2. Now, relating to gradient, which is slope, same thing as slope, some persons call it slope. All right, that is equal to the change in y over the change in x. All right, that's a general gradient formula. In physics, we like to use symbols, so we can use what we like to call a triangle or delta. All right, so as it relates to the equation, that's what's happening there. Now, to find the gradient, you simply take these two values, find the difference of them, which this would be delta y, and then you find the difference of these two values, that would be delta x, and then when you divide the change of y by the change of x, then you would get the gradient of this graph. All right, so as it relates to the gradient, that is how it is found. So the gradient of the graph line gives the value of resistance for the component under investigation. A steeper gradient means a larger resistance. But more importantly, if the current lies on the y-axis, then the gradient is the inverse of resistance. If the current lies on the x-axis, rather, the gradient is the inverse of the resistance. If the current lies on the y-axis, then the gradient is the actual resistance value. Meaning, if I were to put the current here, symbol for current is I, and that's A. And if I were to put the voltage here, V, in units of volts, then what we have found is really I over V, because the gradient, remember, is the change of Y over the change of X. So what we have found is the change of I over the change of V. Now, based off what we already established for Ohm's law, if we transpose for R, we'd get V over I equals to R. But that's not what the gradient is represented here by. It's actually I over V. This is V over I given R, but the gradient of this is actually I over V. So if this is V over R, V over I being R, then I over V must be the inverse of R. All right, so it's very important that you know which axis you're dealing with. If you're dealing with current over voltage, then it works out to be 1 over R based off Ohm's law equation. But if it's a case that you have it as being V here on the y-axis and I here on the x-axis, then we have a different scenario. Here we have change of V over the change of I, and that will now give what we have just seen here, the same thing, which is R. So you can't just jump and say, all right, the gradient is always going to be R. It can be R, it can be the inverse of R, but it will tell you what the resistance is. All right, and here's a typical graph showing the V over I relationship. All right. All right, let's get to that. Good. Now, current over voltage, IV graph, that's I in amperes, that's V in volts, graph line through the origin. And then we have voltage current. So, note the difference. This is a current voltage, IV. This is a voltage current graph. You can put either quantities on either axes, but the gradient will tell you what the resistance is or what the inverse of the resistance is. And you can easily work out what this is, because based off how the graph is shown here, you can see that 1 matches to 0.1, 2 matches to 0.2. You can do it at home. 3 matches, 0.3 matches to 3. So you could easily find what the inverse resistance would be for this. And for the voltage current, directly finding resistance, on the y-axis we have voltage, and the point in between, that's 0.2 matching to 0.1, so 0.2 to 1, 0.4 to 2. So that's a ratio of 2 to 1, so we can just jump and say, all right, the resistance here is 2 ohms for this graph. All right. For the other one, you'd essentially have to divide 0.1 by 1, which would give the same 0.1. So that's 0.1 per ohm because it's the inverse of resistance. And when you invert that, 0.1 inverted gives 10. So this graph shows 10 ohms resistance, or 1 over 0.1 inverse resistance. And then this one now actually shows 2 ohms. All right. Now, looking at Ohm's law in a little bit more detail. Steeper gradient means a greater change of voltage over the same current. This means that one load requires a larger voltage across it to push the same current. Therefore, this load has a greater resistance. So, to delve into that a bit more, looking at two lines. One is steeper than the other. Because a steeper line means that for a given change of x, there's a greater change of y. And if you don't believe me, look at this. If you look at where this line is on the x-axis, you see that the purple line, it should look purple to you, passes through the first point on the y. The same line of x passes somewhere about 2.5. Even better yet, if you look at the second point on the x-axis, you'll see that that passes through the second mark on the y. The same second mark on the x-axis passes through 1, 2, 3, 4, the fifth mark. So we see here that this purple line is a 1-to-1, meaning that one mark here is one mark on the y, one mark x, one mark y. But for the green line, one mark on the x-axis corresponds to about 2.5 of a mark on the y. And when you work the gradient out, if you have a greater number in the numerator, then you have a greater gradient value. So a steeper gradient, steeper slope, means that the resistance, which of course is V over I, is going to be greater. And what this means is just simply that you need a greater voltage to push the same current. All right, because remember, resistance fights current, so if you want to get the same current through, you got to push harder. And that which pushes is, of course, the voltage. All right, now, quick question. Do all conductors obey Ohm's law? You'd be surprised to know that most conductors do not. But why is that? Ironically, most electrical conductors do not obey Ohm's law, even though Ohm's law is the law for all circuits. Devices that do not obey Ohm's law are called ohmic. So you just simply put an IC on ohm, ohmic devices, while devices that do not obey Ohm's law are called non-ohmic devices. So it's ohmic if they do obey, and non-ohmic if they don't obey. Simple, right? Right. The main cause of non-ohmic behavior, meaning that the main reason why some devices or most devices don't obey Ohm's law, is due to what we call a variable resistance. And these devices have a variable resistance as they carry a current or when a voltage is applied to them. So how does this tie now to Ohm's law? From a mathematical standpoint, V is equal to IR. All right? And if you want to, you could say V is equal to RI. Now, if you take R as being a constant, all right, this is math, basics, then we could say V is proportional to I. This is what this symbol means. So that symbol is directly proportional. All right? All of that is just summed up now into the Greek letter alpha. So if it's a case that you want Ohm's law behavior, if you want an ohmic device, then V and I must be proportional where R remains constant. It does not change. If this starts changing, if the resistance starts to change, then the V proportional to I relationship cannot hold. And once it does not hold, then it simply is not an ohmic device. All right? And you'd be surprised at how many devices do not obey Ohm's law. Some do, but not all. So let us look now at a graph or a typical graph of what ohmic versus non-ohmic would look like. So we come back now to graphs. Ohmic resistors. Resistor can be anything that inhibits current flow. Resistors that obey Ohm's law, an increase in voltage creates a linear. Linear comes from the word line. So there must be a linear relationship in the increase of voltage and increase of current. So this is a current voltage graph. Remember, current voltage graphs gives the inverse of resistance. So when you find this graph slope, the line, you have found the inverse of resistance. For non-ohmic resistors, it's not a straight line. simply put. So you can have a curve, you can have a zigzag, whichever way it wants to work out. But once it's not a straight line, then it is non-ohmic in its behavior. All right, so non-ohmic loads, resistors, no straight line or curves. Ohmic resistors follow curves. And here are some graphs, typical graphs of some ohmic and non-ohmic devices. Now, you'd see here that there are 6 shown here. And only of the 6, only one follows a straight line. They generalize and say ohmic conductor. And it can be any device that follows this law. But here we have a filament lamp. So the same thing as the lamps that have the wires in them that burn out quickly. Yeah, those don't follow Ohm law. You might think they do, but they don't. And the reason for that is because their resistance doesn't remain constant. Once they carry a current, their resistance changes because their temperature changes. Resistance is very temperature dependent. So because of that, you find that the curve is as such. Gas discharge tube is the same thing as like, what they call it now, the HID bulbs, yeah? These devices now, they start producing a small current, but over a certain voltage range, the current remains constant and it just shoots up. Thermistor, thermal resistor, something that varies resistance with regards to temperature. When you apply a voltage across thermistors, their response is nonlinear. Thermionic diode, diodes that are powered by thermionic emission or basically exciting electrons, that type of thing. Semiconducting diode, that which is found in electronics. All of these 5, they don't follow Ohm's law. Anything that follows a straight line relationship is an ohmic device. So just please bear that in mind. Now, moving on. Electrical circuits. We're going to look now at a bit in terms of the electrical circuit themselves. An electrical circuit is a closed loop connection, and you must bear this in mind, closed loop, from one terminal of a power source to the other. So power sources have 2 points, where the current leaves and where the current comes back. So once you create a closed loop from one point to the other of the terminals, you have created a circuit, and then this loop has various components linked to it. We're going to look at what the components are. These components include, but not limited to, switches, ammeters which measure current, voltmeters which measure voltage, loads which basically convert the electrical energy to other forms, or any device that stores or uses up electrical energy. Alright, so once you're dealing with an electrical circuit, you must have a closed loop from one point to the other of the power source, and then you have components that are connected and create that loop from one point to the other. So there are 2 types of circuits. First one is a series circuit, the other one is a parallel circuit. Series means in line, so we have the power source, we have the components, and even the connecting wires can be components. So you have the components from the plus side through the lamp, go around, come back to the negative side. Alright, for the parallel now, it modifies it a bit. What we have here is multiple pathways for current to flow. So when the current gets here, you can say, alright, continue, or it can just go down. So once you have multiple pathways, then it's parallel. If you only have one pathway, then it is series, as it says here. This circuit arrangement is one where all components are linked end to end along a straight path between the terminals to form a circuit loop. Alright? Current flows through the circuit along this path alone. And any discontinuation or break at any point along the circuit results in no current flow through the entire circuit loop. So one thing, looking at the circuit here, all components are linked end to end. So the battery links to this, that end links to that, so on and so forth. The switch here and it comes back. Current flows through one path only, from battery to bulb to switch back to battery. Any discontinuation results in no current at all. So if you remove the wire from the battery, no current. If you take a bulb out, no current. If you remove the switch, no current. Once you create a break, there is no current to flow through a series circuit. Now, this is a bit to kind of absorb, but I'm just going to run through it real quickly. The voltage, current, and resistance are all affected by the type of circuit. Voltage. Total voltage applied to the circuit is equal to the sum of the individual voltage drop across each load. So what this is saying is that if you supply a voltage to this takes some, that takes some, and even the wires, but we're going to ignore those because they have negligible resistance. So whatever voltage is supplied, this will take some, that will take some. So when you add whatever these take, you'd get back what the voltage of the power supply would be. So that's why it says voltage total is voltage 1 plus voltage 2 plus voltage 3, any number of components, you add them and you can get back the total voltage that is present. For current now, the total current supplied is the same at all points within the loop, and every load or every component experiences the same current. So what they're saying is that the current here, same current here, same current here, anywhere you want to take it from, the same current will be found within a series circuit. For the resistance, total resistance is the sum of all the individual resistances in that circuit. So the bulb is a load, it provides resistance. The bulb, again, 2 bulbs. So if you want to find a total resistance within the circuit, you'd have to know the resistance of this bulb, resistance of that bulb, and any other component that provides significant resistance, and then you just add all the resistances within that circuit. And can I tell you that a battery has internal resistance? Yeah. It's not a perfect conductor, so it provides some level of resistance for itself. So, in summary, voltage total is voltage plus voltage 1 plus 2 plus 3, yada yada yada, on the way to however many voltage components you have. Current is the same throughout. Resistance is just simply adding the value of resistances that are there. And N here is just the number of components that you're considering. Now for the parallel. This circuit arrangement now, it forms a loop, but there are more than one pathways for the current to flow. Current flowing through the pathways can flow through each component individually. And what we have now is what we like to call a junction. Now a junction is just like what they would say in traffic law. You come to a point, you can either go left or right. That's what a junction provides. So when we look at the circuit here, the switch, when it is on, current can flow through the bulb, and its way can flow through what they call a solenoid, and its way can flow through the motor. So it can flow through each of these individually, but coming from the same source. So that's the main difference between a series and a parallel. Series has one way, parallel has multiple ways. The rule for this, the voltage from the battery is the same voltage across each load. So if this battery provides 10 volts, the bulb gets the 10 volts, solenoid gets the 10 volts, the motor gets the 10 volts. In terms of the current now has to be split, because you'd imagine once you have a junction, charges are flowing, all of them won't flow through the bulb. Some will go through the bulb, then onto the solenoid, then from the solenoid onto the motor. So the currents must be added in each of the junction. For the voltage, it's the same across each component, but for the current, you must add the currents for each junction point. In terms of resistance now, most students have a challenge with this because it doesn't seem to make sense, but based on how it derives, we realize that the resistor total is actually the inverse of the total resistance equal to the inverse of each individual resistor that is present there. All right? So really and truly, when you're working out the series parallel, and that's a series parallel, we'll get to that. But just know that when it comes on to the resistors in parallel, it is not the same as with resistors in series. So just a quick recap, voltage here. For series, you add the voltages of the components, current is the same, resistances are added. For parallel, the voltage across each component in the junction is the same. Current is not, is the sum of them, and the resistances are the reciprocal. All right? So voltage for the parallel, the voltage provided by the battery is the same voltage across the bulb, the solenoid, the motor. Remember that. Current is split. So whatever current comes through here, whatever is provided by the battery, a portion comes through the bulb based off its resistance, a portion goes to the solenoid based off its resistance, and then the remainder goes through the motor. And of course, the resistance, and we'll work out a question with this, is just really the reciprocal working out. So when you compare series, it's the same, similar thing, but we have just reciprocated the values. Now, we can have a situation where series and parallel combine, and what we simply call it is series parallel circuit. And most circuits will have this arrangement because it makes sense to have it because you combine in the best of both worlds. So this circuit is a combination of a series and a parallel circuit that operates as one and is powered by the same source or sources. Alright? The rules established for series circuit and parallel circuit still apply strictly to its behavior. So whatever you know for R1 and R2 in series, and whatever you know for R3 and R4 in parallel, will apply strictly when you're dealing with a series parallel arrangement. But there will be, of course, a slight modification when you want to find the total resistance, total voltage, total current, so on and so forth. Now, highlighting the series circuits. In a series circuit, there's only one pathway for the current to take. Advantage is simply to design and build. So when you're doing labs in class for CSEC physics, fifth form and such, the simplest circuit you build is just from the power supply to the components back to the power supply. Simple and easy. Disadvantage, however, if one light or one component stops working or if one light goes out, they all go out. Remember I said that for a series, they're inline. So if one is not working, then it messes up everybody else because no current can flow through a gap. Alright? They become dimmer or they don't work any at all. Advantage and disadvantages of parallel circuits. Advantages. If it were light bulbs that were the output devices linked in parallel, if one bulb broke, then the others will continue going. Also, the brightness of the bulbs will be greater than the brightness of the bulbs in series. So, when you really look at it, you may ask the question, well, alright, what about the wiring of our house? Your house. Is it series or is it parallel? If you said series, you'd be wrong. To an extent. Because really and truly, the wiring must be arranged in such a way that they work independently. You don't want to switch off one switch in your house and everything goes dark. Alright? So what we have is that they will wire your house electrical connection to be parallel in arrangement. But you do have multiple outlets on a given junction point or a given leg. So you'll find that the plug and one light bulb may work together, because when you flip the circuit breaker, yeah, everything for a section goes out. But essentially you'd want parallel wiring in your house because it makes sense to just have the parallel wiring instead of a series. Disadvantages. There could be a risk of fire in some cases. Another would be if you have multiple power sources, the power stays at the same voltage as that of the single power source. In parallel, increasing the number of output devices does not increase the resistance as it does in series. So if you have a current issue, an overheating issue, you don't want to really consider the parallel arrangement because, can I tell you, the more components you add in parallel, it actually reduces the resistance. For series, adding components, resistance goes up. For parallel, adding components, resistance goes down. So you have to bear that in mind when you're working or wiring a parallel circuit. Now, points to consider. In series, there's only one part. For parallel, there's two or more parts. Brightness of bulbs as it relates to series and parallel. If you add more bulbs, they get dimmer because they're less current. For you, when you add more bulbs to a parallel, they get brighter because remember, adding components reduces resistance, therefore the current value effectively can go up. If one bulb is removed or damaged, electrical current cannot flow in a series because you have broken the circuit. For parallel, you can have the other components, the other legs or the other connection points going even if one blows. And the application, there's not much for the series, but for the application, it's mainly in wiring of houses, twinkling lights, bumper cars in fun fairs, and even in your car itself, you have different fuses, different links, different connections. Alright, now, let's see if we can put all of this into perspective from a workout standpoint. We have here, as you would have seen already, a series parallel arrangement. So R1 connects to R2 and 3, which are in parallel, and then it comes back now to R4. So this is a series parallel arrangement. Now, we know, based on the question, that the voltage provided from the battery is 12 volts. And we know that R1 to 4 all have the same resistance of 3 ohms. Good? Now, what is the total resistance in the circuit. Now here's how this works out. We have a series parallel arrangement. If it was just series, we would just say R1 plus R2 plus R3 plus R4, but we can't do that because we have a parallel arrangement and that's reciprocal and all of that. So what we have to do is to work it out separately. So work out the parallel section first. All right? So for the parallel section, 1 over RT is equal to 1 over R1 plus 1 over R2. Since R1, R2, 3, and 4 are the same, we can just jump and say 1 over RT is equal to 1 over 3 plus 1 over 3. And once we're adding fractions, we find the LCM, which works out to be actually 3. So that's 1, that's 1. So that gives you 2 over 3. Now, please, pay attention to this. 2 over 3 is not the total resistance. 2 over 3 is actually the inverse of resistance. So do not leave it like this. You get it almost wrong because they may be lenient with you. To find the actual value, we say RT, and if you want over 1, is equal to 3 over 2, and that would give us 1.5 ohms. So this is the resistance of the parallel section. So once we have found the resistance of the parallel section, we can now say, all right, 2 3 ohms resistors in parallel works out to just be like a single 1.5 ohm resistor. So essentially, we can replace the parallel section now with a single 1.5 ohm resistor, and diagrammatically it would work out to be something like that. Alright, so we have taken the 3 and reduced it now to just being 1.5. So the total resistance of this entire circuit is 3 plus 1.5 plus 3, which of course is 7.5 ohms. So we have found the total resistance. That's 3 marks. I hope that was simple enough. Now, the current drawn from the battery. We're recalling Ohm's law, V equal IR. So we could say that the total voltage times the total current, voltage total is equal to current total times resistance total. We know the voltage total of 12 ohms. We know the total resistance of 7.5 ohms. So we just need the current, which is what they asked for, current drawn from the 12 volt. So that's equal to voltage over resistance, which is of course 12 volts over 7.5 ohms, and that gives an answer of 1.6 amperes. So that's another 3 marks in the bag for a really, in my estimation, simple workout. All right, now the last part of the question, it asks the voltage across R2. I don't know if you're seeing that, but it's actually R2. So we now have to consider the R2 component by itself. Now here's how this works. Let me just redraw this so I can be very clear with this. When it comes on to looking at a resistor in a series parallel arrangement, the rules that we established earlier on must apply. Alright? So here's what is happening here. This represents our battery. Alright? Now, the voltage from this of 12 volts will have to be shared across this, and across that. So one portion goes here, another portion goes here, and of course another portion goes here. Because remember, we have just reduced this now to a series of 1.5. So we have now considered this series parallel to be just a series of 3 ohms, 1.5, 3. So because of that, we apply the rule for series circuit and say that, well, this will take some of the voltage and the remainder will go here. So to simplify what portion goes here, we can say, well, voltage for the parallel section is equal to the current total times the resistance for the parallel section. All right, applying Ohm's law. We know this to be 1.6 and we know this to be 1.5. All right, so when we put those two together, we can find what the voltage across that would be. And once we know the voltage across that, then we can go to start working on the voltage across R2. This is the one we want right here. Is it? Voltage across R2. And once we know the voltage across the parallel section, remember, the voltage across the parallel section is the same for each component. So once you have found the voltage across the parallel section, then you would have found the voltage across R2. Because the same voltage goes to R2 and goes to R3. Alright? As it relates to that workout. Alright, now current flow within a given circuit can either be constant from one terminal or go in both directions or changing continuously. But as it relates to Ohm's law, there's another question that I'd want for you to work out. If you want, I can provide it due to the social media channels, but we don't have much time to work that out right now. So I hope that what we have gone through, you get a basic idea as to how these things will work out, and I hope that as you work and practice, you'll get better at it. So that's all for today for CSEC Physics Ohm's Law. We hope that you've grasped some of the points that we have discussed.